So op amps are not actually ideal, which everybody who lives in the real world knows that nothing is ideal. We've talked a lot about the characteristics of ideal op amps and the characteristics of op amps in circuits with negative feedback that act like ideal op amps. And what I'm going to talk about this morning is how they are not ideal. Most of this, not quite all of it, but most of this is just theoretical for your knowledge. Some of it is not. Some of it you actually have to remember. But basically, if you need to design a circuit with an op amp in it, there's going to be a trade-off between how accurate your circuit is and what parts you can actually get. So a lot of times, if you're designing, say, a circuit and you need a certain resistor, you can't get specifically the one you want because they don't come in all values unless you get an adjustable one, which takes up a lot of space. So generally, you always in design have to make trade-offs, which, because I had a background in engineering technology, I know that a lot of times things don't work the way you think they're going to. And it's important to understand ways in which it won't work the way you think it might. So using the right op amp for design is a good idea. They all have specifications and they all have limitations and advantages and disadvantages. In here, we use the same op amp for everything. It's a reasonable, 741 is a reasonable op amp. It's not expensive. It works for what we do. It has some limitations as far as speed and frequency response, but other than that, I mean, none of those things matter in here. So we use that. They're inexpensive, so when you blow one up, I can always just go get another one and give it to you, and it's all good. But there are different characteristics that go with every kind of op amp you get. There's, frequency response or whatever the open loop gain is. Remember I said for ideal op amps it would be infinity. We know it's not really infinity, and it's large, but it's different depending on what op amp you use. Use of a data sheet helps a lot because it actually gives you some of these parameters. And I'm going to just talk about a couple of things that you should be aware of in dealing with op amps. So there are a couple of practical considerations to make that may or may not matter depending on what kind of circuit you are designing. So the important things to know about, and I'm not going to cover everything on the data sheet because that would take probably a whole course to cover, but I am going to cover the most important things that you should look for when you're using a data sheet. One is input offset voltage. You would assume that at the inputs, because we always say that the voltages are equal, that there would not be any voltage between the two terminals. And the reality is there is a little bit. And that's basically just a DC balance, and it can have an effect because it gets magnified at the input and appears at the output. It might not get magnified enough to matter, but it can. So that's one thing we will look at. The other is input bias currents. Those are currents that are going around inside the op amp when you connect your DC, your plus and minus DC. There's currents going all over the place inside the op amp, and we assume that the current going into the two terminals is zero. But there is actually a little bit of currenting going on that, again, can be sources of error depending on what kind of circuit you do. And the last thing is slew rate. That's basically how long it takes to change voltage at the output. So how long it takes to change from 0 to, say, 10 volts. And you would want it to be instantaneous, but in reality, there's a certain amount of time that it's going to take. Most of the time, you don't notice it because everything that we're doing is slow enough that you can't see the slew rate limitations on your op amp. I think I had one occasion as a student many years ago where I did something with an op amp and you could actually see the slew rate limitation on it because I was trying to do something too fast for the op amp to keep up. But most of the time it's not a big deal unless, depending on what kind of output you need and what kind of speed response you need, it could make a difference. So these are the things that we use to represent those errors. I'm going to talk about slew rate separately later. So all I'm going to talk about at the beginning is the input offset voltage and the two bias currents that may occur at each input. What we do to model how this works is we basically take a voltage source and we label that VIO, which is input offset voltage. It's really small. We also label a current source at the input for both the input bias current at the inverting terminal and the non-inverting terminal. And then we put an ideal op-amp in there. So basically that is modeling what's going on inside the op-amp by putting an ideal op-amp with sources outside so that we can kind of see how they work. So in reality, and this is how we kind of deal with these, if we have a zero input and we have a closed loop op-amp and we have nothing going in, we should get nothing coming out. But in reality, the presence of those offset voltages and currents can be amplified and appear at the output as a voltage, whether it be the currents, the voltages, or whatever. Now, sometimes they cancel each other out. We would like it if they would cancel each other out completely. And there are ways to kind of make them cancel most of their selves out. So we'll look at that in a minute. So this is only a problem when you're amplifying DC. When you're amplifying AC, this really doesn't matter. If you have DC and you're amplifying AC, you can just filter the DC out. So that part doesn't make any difference. You can just run the signal through a capacitor, all the DC will go away, and you'll be fine. But if you're amplifying a signal that's going to come at the output to be rather small, then it can make a big difference. So for large DC outputs, again, it doesn't really matter. But for small DC outputs, this can make a difference. There is a data sheet that will give you these values. They're kind of worst case values, but they're not listed exactly in the same way that I just told you what they were. So if we look at a data sheet, the input offset voltage is easy to find. You can look at the top of the data sheet. It tells you what it is, and it's telling you it's a typical value of 1 millivolt, and it can be up to 5. And you know, that's really tiny. But if you magnify that by a great deal, that could be actually significant. So depending on the type of circuit you're using, that can make a difference. The offset bias currents are given to you as an average and a difference. So IIO is labeled as the input offset current, and that's basically telling you what the difference is between the two. And then IB, the input bias current, is giving you the average. So the average input bias current for this is typically about 80 nanoamps, and then the difference between them is typically 20 nanoamps. So that kind of gives you an idea. Again, these are really small. These are not big. It just depends on the kind of circuit and how much amplification you're using to see if it makes a difference. So we're going to look at how these work in the circuit. We're going to use superposition, so we're going to use each one individually and kind of see what their effect is and see if we can figure out what the overall effect would be. So first of all, we're just going to look at VIO, and that means we're going to turn off the two current sources, and we basically just get rid of them because they're open circuits, so they just disappear from the schematic. And now what you get is a non-inverting op-amp circuit. The voltage right at the input is going to be VIO, and RC, does that have any effect on the circuit right there? No. It's basically, we just don't even consider its presence at the moment, so we don't worry about that. So all we do is basically, we know that VIO is going to appear at the negative terminal, and then we just multiply that by the gain, and that gives us the output voltage just due to that offset. And you'll notice that we look at the magnitude of it, and the reason we look at the magnitude is because we want to come up with kind of a worst case scenario, because you could have a positive voltage from one thing and a negative to the other, and like I said, they can cancel each other out. But if we look at this and look at just the worst case, then we can actually kind of figure out how this works better. So we're going to look next at IB minus. That's just one current source. And what we have there, first of all, RC still doesn't have an effect on the circuit. So we've got 0 volts at the point of the non-inverting terminal. And basically, what we have is current that is flowing out of IB minus. Is it any current going through RI if it's got 0 volts on either side? No, there shouldn't be. It's got 0 volts on the right and 0 volts on the left. So no place for the current to go through RI, which means it can't go into the op amp and it can't go through RI. So the only place the current can go is kind of around that loop to the output. That's the only place the current can go. So that means there's just one current, and that's IB minus. So that means the voltage that appears at the output is just, using Ohm's law, going to be IB minus times RF, but the current's going to be going opposite to the direction of the actual voltage. So we're going to get minus RF times IB minus, and that gives us how much that particular offset is being used in the circuit. So that's 2 out of 3. And RC still hasn't had a point in being in the circuit yet. It's been neglected twice. So now, when we look at IB plus, that is where RC actually has an effect. We've got a current coming into this node, and it can't go into the op amp because there is no current going into the op amp, which means the only direction that current can go, IB plus, is through that RC. We actually call that a compensating resistor. It actually has a name. So that current will go through that, which means that IB plus is going through RC, and the voltage at the terminal that is non-inverting is RC times IB plus. And that is just going to get multiplied by the non-inverting gain of this op amp, because it's going into the non-inverting terminal, so that's just 1 plus RF over RI. So what that means is, again, we have a non-inverting op amp, it's multiplied by that value, and I did split up the RC and the IB plus for reasons that will become apparent later. Now, all we have to do is combine all those effects, and we can say this is the worst case scenario that we get. So we combine them all, put them all together, and what we end up with is one equation that gives us the magnitude of the error. So we just basically added everything up. And you'll notice that RC is in that equation. So why is that there, and what value should it have? Because its value is going to make a difference in this particular equation. So RC is a compensating resistor. What it does is it tries to limit the effects of the input bias currents. And what we do to figure out what value it has is we want to set the error of the bias currents to 0. So we want to set that whole bias current part to 0. So that would be kind of this part of the equation. We're also going to assume that those two currents are equal. They're not exactly equal, but we're going to make that assumption. So already in making that assumption, we've eliminated some of the good that RC will do because they really aren't equal. So there's going to be a little bit of error still coming through. But we can take RF over RI plus 1 times RC times IB plus minus RF IB minus, and we set it equal to 0. And then we just move things around a little bit. So we put the IB plus equation on one side and the IB minus on the other. And since we assumed that they were equal, we can actually get rid of those currents. So we can take them out. Then we've got RC times 1 plus RF over RI equals RF, so we just solve for RC. And what it ends up being is that compensating resistor should be the feedback resistor in parallel with that input resistor. And there's already a problem with that, because anytime you take the parallel equivalent of two resistors, you're going to get a value that you can't find, unless you have some really, really special resistors. If you can possibly find two 10Ks and take them in parallel and then go find a 5K, but that's generally the way the circuits, they don't work that way. So already there's going to be a little bit of trouble finding a compensating resistor that has that exact value. So because we made the assumption that the bias currents were equal, and because we can't find exactly the right resistor, there still will be error, but it will be minimized as possible. So that is why that resistor appears there. It seems to have no use when you're analyzing the circuit, but it's there to prevent error. It's not there to actually affect the outer part of the circuit that we're building that has gain and all that. So what do you do if you have no data sheet? What if you have an op-amp and you need to use it and you don't know what data? Of course, nowadays you can generally go online and find one. 20 years ago you couldn't do that. You actually had to go and ask for one or go find one. But so maybe you don't know what kind of op-amp it is and you can't figure out what the values are. So if that's not available, you can experimentally, relatively easily determine what these values are. It's not actually that difficult. The first thing you would do is you would connect the op-amp as a unity gain buffer and measure the output resistance. If you do that, the only voltage that could possibly appear at the output would be VIO. It would be really small, but it could be measured with the right multimeter without any trouble. So this is connected such that there's 0 going in and 0 being carried to the output, except the output isn't quite 0. So that would be the first measurement that you would make, and then you would know what VIO was. Then, if you add a resistor to the input to the positive terminal, you can measure the output and solve for IB+. So you get another voltage at the output, you know what VIO is, you know whatever resistor you use, and you have to use a fairly large one to drop voltage, because these are tiny currents. So you have to use a relatively large value of resistance. You can do that and solve for IB+. Then we just put a resistor in the feedback path, and again, we can solve for IB-. It's a little bit different equation, but it's not that difficult. And this is something that we used to actually do 20 years ago relatively frequently. You could figure these things out. It only takes a couple minutes, and then you can figure out what those offsets are. So I'm going to actually show you an example of how to do that. So this is an unknown op-amp that was measured 3 times. There are 3 different measurements made, and from those we're going to determine what all of those values are. So in the first circuit at the top, there is no resistor in the circuit. There's 0 going into the non-inverting terminal, which means whatever's at the output is VIO. So VIO is just going to equal 5 millivolts, because we read that. It's easy. For the second circuit, we've got minus 13 millivolts. So what that means is minus 13 millivolts is going to equal VIO, which was 5, and then minus whatever R is times IB plus. So IB plus, we're going to have 5 millivolts minus 300K times IB plus. And when we solve that, we actually get 60 nanoamps for that value. Then for the third circuit, we can find IB minus. We have, and I'm going to write underneath it so I don't run out of room here. We have 19 millivolts equals VIO plus R times IB minus. So that equals 5 millivolts plus 200K times IB minus, and IB minus equals 70 nanoamps. Finding IB and IIO, all we do is find the average. So for IB is just going to equal IB plus IB minus over 2. And when I get the average, I get 65 nanoamps. And then IIO is just the magnitude of the difference between them. So we don't care about signs. So the difference between them is 10 nanoamps. So if you were to find a data sheet, it would give you IB and it would give you IIO, but it would not give you the individual values, but it would give you an idea of how that worked. Slew rate is a little easier. It doesn't actually involve any calculation whatsoever. All it means is the speed of response. So basically the time that it takes to get to a certain voltage is the slew rate. The slew rate is the volts divided by the time. So it's volts usually per microsecond. So V out over TSR is going to be the slew rate, and the slew rate is listed in the data sheet just as it is. So it's given to you generally in volts per microsecond, and that can give you an idea of if you need the signal to reach its maximum in a particular period of time and do it quickly, you do need to know what that value is. So it's easy to find on the data sheet. In this particular op amp, this is the one that we pretty much use, it's half a volt per microsecond. So that still seems really, really small, but since everything runs so quickly nowadays, that can actually make a difference if it doesn't get to its output voltage fast enough. All right, the last non-ideal effect. I told you there was only 2, but I actually talk about one more. And that's what we do when the open loop gain is not infinity. Because how does it actually affect the circuit? Because we know that it does. And I am going to mathematically derive how it affects it, but you really don't need to pay attention. Well, you do need to pay attention. Never mind. Forget I said that. You need to pay attention, but you don't need to really remember what the concept is until the very end, because you'll see how the actual gain equations we use are incorporated into the equation that includes the gain when it's not actually large. So we're going to look at a situation in which the open loop gain is not infinity, which, like I said, we already know it's not infinity. But if it's finite, then those two voltages, V minus and V plus, aren't equal. It basically means all the stuff that we learned about op amps isn't true, or is less true than it was. So we actually have to go back to the op amp model, which I'm not going to show you. I'm just going to say this is where this comes from. But V out is going to be whatever that open loop gain is times the difference between the two voltages, because they're no longer equal. So if A is really, really big, like 100,000, then it's really not going to have that much of an effect being finite. But what if it's 5? Then it's going to have actually a major effect on the output. So if it's not, then this is what happens. If we have this circuit connected, we know that V2 is 0 because it's connected directly to ground. That's all that is. But we don't really know what V1 is, and we don't know the difference between them. So we're going to have to figure that out. We know that V out is A times 0 minus V1, and that means minus A V1. So V1 is going to be minus V out over whatever A is. If A was really, 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 really large, then V1 would come out to be 0, just like V2, and we'd have an ideal op amp again. But as A gets smaller and smaller and smaller, the value of V1 starts to become more and more different from V2. Okay, I1 is Vin, which you can see, minus the voltage on the other side of R1, which is minus V out over A, divided by R1. And then we can simplify that just a little bit. And then I2 is going to be minus V out over A, which is the voltage at the left side of R2, minus V out, which is on the right side, divided by R2, and we can simplify that a little bit. Now, if there's no current going into the op amp, which we're assuming there is no current going into the op amp even though the voltages are different, if that's true, then I1 and I2 are equal. So we can set those two messy things actually equal to each other. So when we do that, we get Vin plus V out over A all over R1 equals minus V out times 1 plus 1 over A all over V2. We're getting there. We take that, and we're going to multiply both sides by R1, R2, so we can get rid of the big fractions. So we're going to do that, and we get R2 V in equals R2 V out over A, and that equals minus R1 V out times 1 plus 1 over A. Yeah, we only have like 2 more slides to get to the end. It's basically just algebra, though. So we're going to take that, and we're going to separate V out and V in, because that's what we need to do. We need to figure out what the overall gain is. So we need to separate V out and V in, and when we do that, we get R2 over A plus R1 times 1 plus 1 over A, all times V out, equals minus R2 times V in. So then if we put V out over V in, we just get minus R2 over A, blah, blah, blah. Doesn't look like anything we've had yet in here. And it doesn't quite, but it will in just a minute. Do one more thing, and then we will make it look like something you've seen before. We take that, and what we're going to do is just do some moving around and simplifying just a little bit. So we're going to take R1 and we're going to put it into the equation there in R2, and then we're actually going to take R1 out and look at what we have. We have minus R2 over R1 on top. That was our original gain when we did an inverting op amp that was ideal. So that is the actual gain of the op amp if A is infinite. So if A goes to infinity, then the answer is just minus R2 over R1. If A is finite, then you use this to adjust it. So that's why I'm saying you only really need to remember what I just got to. That's the actual way we adjust for non-infinite gain. In gain values that are really large, like I said, doesn't really matter. But if the value was 5 or 10, then that would actually make a significant difference in the gain. The interesting thing is that this whole idea carries through to any amplifier configuration. So if we make a non-inverting op-amp, we actually do the same adjustment, and I'm not going to go through and derive it again because it would take too long. But basically, if we have a non-inverting op-amp, the same gain is on the top, the 1 plus R2 over R1, and we do the same adjustment to it that we did to the other one. So what's in the denominator of the fraction is always how we adjust for non-infinite gain.